All right, this is session number 5. The first thing we're going to do is go over quiz 3 solutions very quickly. Overall, you guys did really well. Some minor mistakes here and there, so we'll go over that. The first problem was about basic vector operations. We have our vectors resolved in components AB and AC, and we were to ask to do basic vector operations. So for part A, we get this vector 3ab minus AC. Nothing too difficult here. Everybody got that one right. Then for part B, we needed to compute the vector first, then compute its magnitude. And one comment that I'm going to go ahead and make here, that magnitude is not distributive, right? So if you were to compute the magnitude of 2ab first, and then compute the magnitude of 1/2 AC and then add them up, you do not get the same thing. So that's what I was testing here, okay? We need to find this expression 2AB plus 1/2 AC first, then we compute the magnitude, okay? So that's a minor mistake here. Vector U, that's a unit vector in the same direction as BC. That's pretty straightforward. Everybody got that one right. So you have your unit vector. No, you have your regular vector. You find the magnitude divides the vector by the magnitude. Okay. And then the next problem, that's where different answers were given by different people, which is completely fine. It was asking to compute or to determine a vector that's orthogonal to vector AC. Many different ways to compute this vector. Okay, it's not unique. There's many vectors that will satisfy this condition. So some of you found a cross product with another vector. That's no problem. You can do that. Or you could also pick any vector such that the dot product is 0. Okay, and you can just pick a couple of values. Let's say, I picked 1 for the third component, then the other 2 are determined. Okay, you can figure it out algebraically and check that the dot product is 0. So in my case, AC is orthogonal to V. And again, all of you guys got this one right. You just had different answers, which is to be expected. For part E, here we were asked to compute the angle B, and some students had correct step, but you did not compute the correct angle. So vectors BC and BA, those are the vectors that form angle B. So we have to be careful what we choose here. Okay, some people chose AB and AC, but those vectors do not form the angle B, right? Okay, so not only do we need to know how to do it, which is computing the dot product and then using the geometric definition of the dot product to determine that angle. Okay, we also just need to be careful of which vectors we're using because you will get different answers. Okay, so that's problem 1. All right, let's keep going. We'll go through all of them and then we'll discuss any questions you might have. The second problem was an application of cross product. No problems here. We needed to compute the cross product of 2 vectors and then just find the magnitude. Some of you gave me approximations. That's fine. You can just leave it as is. Some people simplify it. Again, I'm not too worried about the form of your answer, numeric answer, as long as all of the steps are done correctly. Okay, and then the last problem, we needed to come up with an equation of a line in 3 space. So this is a parametric vector form of a line with given conditions, right? So we had a point and we needed to find the direction vector. So this is a cross product. Carefully compute that cross product. And then we put it together. We'll put it together in this form where we have the initial vector for -5, 2, and then my direction for the line. Okay, so here I'm also giving you a warning. I saw a couple of students just taking those numbers and just plugging them in, as you know, the one in red that I'm showing to you that some students do. That is not incorrect. Okay, we need a point, we need a direction. We can't just randomly pick those and put them in this equation. Okay, so that's your solution for problems 1 through 3. Let's take a moment here, um, review any of this, and let me know if you have any questions.
How did you get -17 as the I component for the direction vector in question 3?
So 2 times -4, right? 2 times -4 is that's negative, let me see, 2 times -8, and then -6. Oh, -9, sorry. Is that not right?
Oh, right. No, I did the exact same thing. I did -6 and got -14. I see now. It was
Okay,
just a
okay,
stupid
yeah,
mistake
yeah.
on my end.
Yeah, so sometimes
Thank
you just
you.
gotta write it right? So like, see, I said it
Yeah.
wrong, and I'm like, wait, that doesn't sound right. Okay, and that's
Thank
what
you.
I mean. Like, I make these mistakes all the time if I rush through them, right? So just take the time to set them up, and these algebraic mistakes that can happen. That's fine. But it makes, you know, what 5 seconds to just set this up, and then you get it right. Yeah. Okay. All right. Any other questions? Nothing? Okay, then let's go ahead and switch to what's on today's agenda. Okay, so 3 things that we're going to cover today. We're going to discuss quiz number 3, which we just did. So that's done. Okay. New material will be sections 13.6, 14.1, and 14.2. And while 13.6 is a section in this last chapter 13 that's on your test, the actual section 13.6 is not on the test. So let me go ahead and make a note. This is not on the test, not on any test. Okay, so you might be asking me, why are we covering this? Okay, so this is one of those sections that's kind of like more of an FYI section. And we don't need to test our knowledge of these equations that we're going to discuss in a minute, because they're out there. We can just retrieve them. We just need to understand these three-dimensional objects that we will encounter in later sections. Okay, but it is more of a supporting section. Okay, you do still have online homework that's not very complicated, but I will not put any of these problems on either test or quizzes. Okay, so this section is just needed for us to have a better understanding of the graphs, and especially once we get to um, triple integration, it's good to be familiar with these equations. Now, sections 14.1 and 14.2, that's next module material, right? So that would be on the next test, okay? So what's on this common test? It's everything up until 13.5, including 13.5, but not including 13.6, okay? All right, so let's go ahead and take a look at the basic ideas of section 13.6, which is quadratic surfaces. Okay, I'm going to briefly go through these objects, and you do not need to memorize these equations. You do not need to just be able to determine what it is right away. Okay, in fact, I recommend have this sheet in front of you as you work through problems on your homework. And the best way to kind of practice these problems is just go through my MATLAB problems. They're really good about making this visual representation and connecting um, these ideas of what these surfaces look like. Okay, so have this sheet in front of you, practice some problems, and that's all you need to know. Okay, later on, we should just be able to say, oh, okay, yeah, I remember what this is. This is an elliptic paraboloid. So the first equation is of this form here, ellipsoid, and we can talk about traces. Traces is just the intersection of this object with the plane. Okay, so imagine, let me go ahead and see if I can make a nice picture here. If I were to take a plane and cut this ellipsoid, right? Then the intersection of my plane and the ellipsoid would be this curve, right? Okay, and all of the intersections for this example are ellipses, and you can see you can actually move this plane in any direction you want, no matter which way you're going to cut it, whether it's horizontal, vertical, or you just cut it at an angle, you're going to get an ellipse. Okay, so that's what traces are, and that's what your problems will look like. Okay, they will ask you either to match graphs or to determine what kind of surface this is and talk about traces. That's about it. No computations, and no calculus going on with these objects. Then we have an elliptic paraboloid. So that is an object that we will encounter a lot when it comes to integration. So z is equal to x squared plus y squared. It's a paraboloid that goes upright. You see the whole object sits above xy plane. Okay, so what would be a good example? Just your straightforward example of a simple paraboloid is something like this, right? Okay, we will encounter this particular equation quite a lot. So here we have a and b is equal to 1, right? But they don't have to be. They can be any non-zero numbers. And what are the traces here? The traces here will be parabolas. So again, you imagine you're cutting your, I'm sorry, these are ellipses. So we're not cutting them in that direction yet. If you cut them with z planes, right? So the horizontal planes, then these intersections right here are ellipses. Now you could also cut them in different directions. So if we cut them with x and y planes, then you can see, let me use a different color, that we're going to get these cross section that look like parabolas. Okay, so here's one, the one in red. Okay, so and then you can cut it for y. So this was y is equal to 0. Imagine you picked x is equal to some value, right? So where would that be? That would be somewhere here. So that's the one in green. That's my trace if I were to cut it with x is equal to some value. All right. So that's elliptic paraboloid. Then the next one is hyperboloid of one sheet. So what's the difference here? Okay, so it's hyperboloid of two sheets and one sheet. Those are a little bit different. Okay, so here we have a negative in front of z. Again, these values could be any numbers except zeros. Okay, and again, just imagine you take this object and you cut it with the plane. Z is equal to some number. So that's your horizontal plane. You can see again, you get these circles. Well, they look like circles, but they're actually ellipses, right? Okay, and then hyperbolas, what do they look like? Let me change the color. That would be an object like this, right? Okay, so if you cut your um, hyperboloid with a vertical plane, those are the intersections. Okay, let's see a couple more of these, three more. We have a hyperboloid of two sheets. You notice how the equations are slightly different. It's just the negatives are in different spots. Okay, so what do we have here? Again, what are the traces? We have ellipses and hyperbolas, just like what we've had in the previous example. Okay, elliptic cone, that's something we will encounter. Okay, a lot. That's a good example to kind of focus on. So something like z squared is equal to x squared plus y squared. Okay, that's a two-sided cone, right? Okay, so we will encounter this particular example in future sections. And again, you can see what the traces are. We have ellipses and hyperbolas again. Okay, they're just slightly different looking hyperbolas, right? And then the last one is hyperbolic paraboloid. Ooh, say that many times. Hyperbolic paraboloid, okay? A simple example would be when a and b are both 1, so that's your z is equal to x squared minus y squared. And here we get parabolas if we cut this surface with z is equal to 0, z is equal to value, non-zero. Okay, so we get these parabolas. Let me see if I can, I'm sorry, hyperbolas. The two-sided, right? Here we go. One side here and one side here. And then if we cut them with the other directions, then we get these parabolas. So that would be right here, the ones in blue. Okay, so your online homework will just ask you to take a look at a surface with a given equation, and you just match it to one of these and you determine what they are. Okay, and they're really good about making this visual connections. Okay, so that's it. That's really all we need to know. And again, if you join a little bit later, do not memorize these. Just please have them in front of you. This is a page directly from your textbook, or you can just use these notes. You can have them in front of you on the quiz, on the test, although you're really not gonna need it on the test. Okay. So let me stop right here for a moment. Take a look at these and let me know if you understand the basic idea. Okay, the basic idea of what we've just discussed. All good? Are you guys with me? All good. All right. Then let's go ahead and talk about the next the next material. Okay, so vector valued functions. That's going to be our next chapter that we're going to discuss, and that will be, you can think about it as module 2. Okay, and that's chapters 14 and 15. Okay, for module 1 we talked about chapters 12 and 13. Okay, so what we need to know in this course, okay, in this particular section, we're going to learn about sketching curves in 3-space using a graphing utilities. Then we're going to compute limits and talk about vector equations of lines, which we already know what they look like. Okay, so in general, we need to have this form in mind. R of t is equal to vector function, okay, f of t, g of t, and h of t. Okay, so a curve represented in this form. That's what we need to focus on in the next few sections, okay? And how to work calculus with um, this particular form over a line or a curve, and then how to graph it, okay? So the first thing we're going to do is we're going to sketch some of the vector valued functions. This should be a D, okay, using a graphing utility. And if you go to your chapter 12, 13 folder, you will notice that in week four lecture and class notes, I posted a link to GeoGebra, plotting curves in 3-space. So if you want, you can use that tool right there, okay, to graph all of the curves that we're going to graph in a minute. Okay, I also give you an example of how we graphed one curve, but we're gonna go ahead and discuss our curves that I have presented for you here. So the first one is R of t with components 2 cosine t, 2 sine t, 2. We actually don't need to have a utility to graph this one, okay, we can analyze it and say, all right, what is happening here? What is this curve? We know what 2 cosine t, 2 sine t is, right? Okay, that is just an equation of a circle, right? Okay, so this is circle of radius 2 and it's centered at the origin. Okay, now what about that 2? Now we have this third component, right? This third component is 2, which means all it is, we're just lifting that circle 2 units up in 3 space. Okay, so what your picture is going to look like, let's graph our 3 space here. This is x, this is y, and this is z. And all it is, it's a circle of radius 2 with the center at the origin, but now it's lifted 2 units up. Okay, so let me mark this center right here as 2. All right. Okay. Now you can use GeoGebra to plug in values for your functions, and I give you an example where I just write my so how would I put this into my GeoGebra? Let me give you a syntax. So I would say x of t is equal to 2 cosine t, and then I would say y of t is equal to 2 sine t, and then z of t is equal to 2. That's what I would plug in. Okay, and then you can just copy and paste that r is equal to curve. So let me go ahead and write it here. R is equal to curve. And all of that is posted on Blackboard. It's just in case you don't want to look at it right now, you have these notes. X of t, then y of t, z of t. Okay, and then t, get a range, right? So the range here, yeah, what do we need? We need from 0 to 2 pi, right? Okay, because we know that this is a circle. And so this should generate your curve, okay? But again, for this particular example, we don't really need to use the application to graph it. We know what it's going to look like, but just looking at it, right? Okay, so let's take a look at the next example. Here we have 4 sine t, 4 cosine t, e to the power t over 10. So now, oh, let me switch back to black. Okay, now I'm going to look at this and say, yeah, this is, once again, this is a circle of radius 4 now, center at the origin, 0, 0, okay, except now this third component is not a constant. This third component is a function, and let's think about it. E to the power t over 10. What is the smallest value of this expression? For which value of t? What can it get to? How small can that value be? So this is my question to you. How small? Okay, Sarah says 1. Why?
I was
You're
thinking,
right. Hmm. Go ahead.
yeah, I was thinking, just because a number raised to an exponent that's a variable, like the smallest number it'll ever be is 1 when the exponent is 0.
That's correct. Very good. So it will never be less than 1, right? So we start at 1 as the height, okay? And then it goes up, right? So t divided by 10, yeah, so it doesn't go up too fast, but it's also exponential, right? So t over 10, that's still going to give us really high values of e, Okay, so as t goes to infinity, this number goes to infinity. So what you can think of is this spiral. Okay, so let me put this here. This is the picture that's going to go with the second part that starts at 1. So our height starts at 1 because that's as small as it can get. Let me move it over here. And then it generates this spiral, okay, going this way. Okay, why? Because that z component is a function of t, and it goes up very quickly. So you can see how you can imagine this spiral gets stretched really, really quickly. But that distance from the origin, um, that's still 4, right? That's your radius. That's your radius of the circle. Okay, it's just the height is the one that goes up really, really, really fast. Okay, so a good exercise would be to graph this function using GeoGebra. Okay, so see if you guys can figure it out. Again, just follow these steps. Just follow the example I've provided for you on Blackboard. Okay, and I think there I provided 5 cosine t, 5 sine t, t. Okay, and you can see that it's also a spiral that starts at 5, right? And then I'm sorry, no, that one starts at 0 because we can get value for z is equal to 0. That's just t is equal to 0. That's no problem there. And that growth is kind of constant, right? So z is equal to t. And you can compare the example that's posted on Blackboard to this one. See how these spirals are different. Okay, so that's that. Let's go ahead and take a look at the next example. Okay, so here, okay, let's see, 2 cosine t, 4 sine t, and then the next component is 10, a cosine of 10t. Okay, so now if you were to just have this one, 2 cosine t, 4 sine t, what do you guys think that would look like without the third component? 4 cosine t, I'm sorry, 2 cosine t, 4 sine t. What is that object? Can you think of a name for that? Starts with an E. So we had our circles, right? In previous 2 examples, we had 2 circles. And notice how the coefficients for sine and cosine were the same. Now here we have 2 different coefficients. So it's kind of a circle, but not quite. What is kind of a circle, but not quite a circle? That's an ellipse, right? Okay, so that's an ellipse. Okay, and now imagine you have your ellipse, right? Except that the third component, the height, is not constant. It's a function. It's a periodic function. It's a function that oscillates, right? So your height for this curve is no longer the same as you would imagine, okay, just having an ellipse, right? So let's say it was 2 cosine t, 4 sine t, and for third component, you just had a constant, something like 3, right? All right, that's your ellipse sitting at the height is equal to 3. But now this is a function, cosine 10t. What you're going to get, again, it's not easy to actually graph it by hand, but it's good to analyze these pictures and say, what should I get? Okay, my ellipse where the height is oscillating, the height is periodic. You're going to get this crown looking thing that goes like this. Okay, and it makes sense because really what this is a morphed ellipse. Okay, you took ellipse and then you added third component, which is a function of t, the trig function cosine 10t. Okay, so again, you don't need to necessarily go through a deep analysis of these, but I think it's good to do this to really understand why these curved formed the way they are. Like, why is that like this, right? Why do I have a spiral? Why do I have one spiral that goes kind of fast up into the z direction and another one is not? It's because how our third component functions are defined. Okay, so again, a good exercise is to just graph this, sketch this using that application that I linked for you guys on Blackboard. Okay, but in general, if it's something on a quiz or on a test, I'm either going to give you the curve or the picture of the curve, or it's going to be simple enough to sketch it by hand, something like a line that's simple enough. All right, so that's our sketching of the vector valued functions. Let me go ahead and pause here for a moment. Okay, anything you would like to discuss for this particular um, what is it, goal, our learning objective? Let me know one way or another, okay? No questions? All good? All right. Then the next objective we have is computing the limits or showing that the limit does not exist. Okay. This is a concept that you should be familiar with from Calculus 1, except now we have a vector valued function, which means if the limit exists, the outcome, the result, is also a vector, not a number, right? So we talked about we talked about vectors in calculus 1, and then we also discussed it in calculus 2 when we were doing series and sequences. So now we're bringing this into a three-dimensional space where our functions are vector valued functions. So to compute the limit of a vector value function, we just do it by component. And for vector valued functions to have a limit, every component must have a limit. Okay, so let's go ahead and compute these. The first one is the limit of the following vector value functions, 2e to the t, then we have 6e to the negative t and negative 4e to the negative 2t as t goes to natural log of 2. So by component, which means I can just find three separate limits. So carefully, let's compute these limits. So as t goes to natural log of 2, 2e to the natural log of 2, right? What is that? That's 2 times 2, and that's 4. Okay, so the limit for the first component is 4, and then we just compute the rest of them. Limit as t goes to natural log of 2, 6e to the negative natural log of 2. Okay, I'm going to be careful here. So this is going to be 6e to the power natural log of 1/2, right? Okay. The only way for us to cancel e and natural log if there is no coefficient in front of natural log. If there is one, we got to move it into the power. So 2 to the negative 1, that's 1/2. Now we can cancel it out. So this is 6 times 1/2. We get 3. Okay. And the last one, this is limit as t goes to natural log of 2. Here we get negative 4 e to the power negative 2 natural log of 2. Okay, same idea here. This is negative 4 e to the power natural log 2 to the negative 2. Okay, so what is this? This is negative 4 times 1 over 4, and this will give us negative 1. So the final answer is a vector. The limit does exist. It's a vector with what components? 4, for the first one, 3 for the second, -1 for the third one. Okay, that's our answer. Let me highlight it. Okay, so we were able to just evaluate this function at natural log of 2. There's no discontinuity here, no problem. We just plug it in and find the values. All right, now let's take a look at the next problem. Here, we have to do a little bit more calculus. So this is a good time to revisit some of the limit rules and just in general how to compute limit and how to deal with functions such as tangent of t or sine of t and so forth. So let's see. Here we are going to get some problems. Okay, so let's say the first one is limit as t goes to 0 tangent of t over t. Okay. All right, tangent of 0, 0. We get 0 over 0. This is one of the indeterminate form, so we can apply L'Hopital rule, right? Apply L'Hopital rule. That's my abbreviation for it. Okay. Once we do this, we're going to get limit as t goes to 0, derivative of tangent, that's secant squared, derivative of t, that's 1. Okay. Once we evaluate this, this is secant square of 0, which is 1. 1 divided by 1, we get 1. Okay, so no problem here. This was one of those indeterminate form. We know how to deal with that. Okay, let's take a look at the next component. We have limit as t goes to 0 of this expression, -3t over sine t. Again, this is 0 over 0. We're going to apply L'Hopital rule again. So we get the limit as t goes to 0 of what? -3 over cosine of t. Easy to evaluate. We get -3. And then for the last function, no issues here. That function is defined at 0. No problem. So what is our final answer? Our final answer is a vector, right? Not a point. So we're using triangular brackets with components 1, -3, and 1. Okay, so that's our answer for this particular problem. So if one of these limits does not exist, just one component doesn't have a limit, that means the function does not have a limit. Okay, so there's some sort of asymptotic behavior. All right, so that's computing limits. Take a look at these solutions. Let me know if there is anything you would like to discuss. How we doing, guys? We doing okay? Doing good? Okay. All right. Yeah, give me a sign that I'm still with you because sometimes I'll lose my connection and I never know unless you guys tell me that I'm still here and you're still here. So everything is good. Okay. All right. Then let's take a look at a problem that we actually know how to solve, but once again, we're going to discuss an equation of the line. Okay. So we want to find a parametric equation, a vector equation of the line that goes through this point P, and it's perpendicular to both vectors u and v. Okay, so we know how to do these problems from our previous chapter. But again, we discussed all sorts of lines and curves in this one, so you might encounter an example of this type again. Okay, that's no problem. We know how to do these. So find an equation. Okay, which means what is our general equation? It's not a bad idea before you start working through the problem to set up the general equation. Your answer should have this form right here, right? Initial vector, x null, y null, z null, plus some sort of direction, t times the direction vector, abc. Okay, and t is a real number. So that's our goal. We want to write an equation of the line in this form that satisfies these conditions. Okay, we have a point. So we know our initial vector. So that part is taken care of. We do need to find the direction. And if our line is perpendicular to both u and v, that means it goes in the same direction as a vector that's perpendicular to those two vectors. But that's the cross product, right? So let's go ahead and find the cross product. And again, I make mistakes when computing these, so I'm going to write out all details to make sure that we get the correct answer. Okay, so ijk, my vectors come here, and I'm doing u cross v. You could do it in the other order, that's fine too. Okay, cross product of these, so vector I, we get 1 times 0 minus 4 times -5 minus vector j times 1 times 0 minus 0 times -5, and then plus k, what do we get here? 1 times 4 minus 0 times 1. Okay, so for my j component, I get 20. I'm sorry, that's I component. For j component, I get 0. For k, I get 4. So you can write it either in this form with triangular brackets or 20i plus 4k. That's also fine. Either way. Okay. All right. So that's done. Now we just need to put it all together. So our final answer is r of t is equal to, what's my initial vector? Where do I start? I start at -3, 4, 2. That's if t is equal to 0, that's where we begin. And then we travel in this direction, 20, 0, 4 times t, and t is a real number. Okay? That's going to be your answer here. All right, let me stop here for a moment. Take a look at the solution. If you have any questions, we'll discuss it. But in general, I think you guys have done really well on the quiz for this particular problem, right? But let me know either way. Are we good here? Everything okay? Everything clear? All good? All right. Excellent. Then let's go ahead and move on to the next section. Okay, this should say 14.2, calculus of vector valued functions. And you will notice that none of this stuff is brand new. You know everything to you know everything you need to know to just start jumping into the problems. Okay, we want to compute derivatives of vector valued functions. That's done by component. Okay, if you want to compute the derivative of vector value function, just differentiate each component. We want to compute integrals of vector valued functions. That's done, you guessed it, by component. Okay, and determine unit tangent vectors. Okay, unit tangent vectors. We know how to find the tangent vector, right? So that's find the derivative. Okay, and then what? Unit. To take care of the unit part, then divide by the magnitude, right? This is my plus. Okay, compute the derivative. of your vector valued function, evaluate it at the point, right, whichever point that we're working with, and then find the magnitude, divide by the magnitude. Okay, so all of this stuff is really just revisiting calculus 1, not even calculus 2, in higher dimension. Okay, let's review our calculus 1 skills. Differentiate the following functions. So let's do r prime of t by component 4 prime, that's 0, right? Then here I have 3 cosine of 2t, so I'm going to apply chain rule, right? Get negative 3 sine of 2t times the derivative of the inside function, that's 2. And then same idea here, this is 2 cosine of 4t times 4, so our derivative is 0 for the first component, negative 6 sine 2t. Second component, positive 8 cosine 4t. That's our last component. Okay, so derivatives of constants, derivatives of trig functions, and chain rules. So that's what we've applied from calculus 1 here. Okay, let's see. Let's take a look at the second one. R prime of this function. Okay, let's see if you guys can help me out. What is the derivative of this expression, t plus 1 to the negative first power? What do we get? Okay, I see Raymond saying it's negative t plus 1 quantity to negative 2 power, right? Very good. Okay, so here we just apply the power rule. Negative 1 goes up front. The new power is negative 2, also chain rule, but the derivative of t plus 1 is 1. Okay, good. What about the next one? Tangent inverse of t. What is the derivative of that function? Okay, I see an answer. 1 over quantity, right? 1 plus t squared. Okay, so the way I think of tangent inverse, it's 1 over 1 plus stuff squared, right? Whatever that argument is, that's my stuff. The derivative of t in this case is 1, so that's it. That's your very original formula for tangent inverse. Okay, and then what about the last one, natural log of t plus 1? What is the derivative here? Derivative of natural log of t plus 1. 1 over t plus 1. Very good. Okay. So it might have been a while, right, since we've done these operations of differentiation and integration, which is the opposite. So do a self-assessment. Think about, okay, what is it that I need to review? Maybe some of you feel very comfortable with just computing derivatives. If not, let me know, and I can give you some review exercises, even through my Pearson or through my MATLAB or just by hand. Okay, but it's a good idea to just kind of think about, okay, is this stuff that I remember, or do I need a quick refresher? All right, so differentiating done. Then the next logical thing to discuss is compute integrals. Okay, computing integrals also by component. Okay, so this problem says compute the integrals of the following functions. Let's go ahead and take a look at them. Let's see if we remember our methods of integration. So the first integral, t e to the t dt. Okay, this is one of those popular examples that we discuss when we talk about a very specific method of integration. Do you guys remember how to integrate this one? T e to the t. What is the method? This one is done by parts. Very good. So by parts, if you don't recall, I'll give you the formula. We have integral of u dv is equal to u times v minus the integral of v du, right? So this is the format that we should follow. Okay, so for my function here, I'm going to set u is equal to t, which means du is dt. That's the part where I set one function to be u and then find its derivative. What about my dv? E to the t dt, that's going to be dv, which means v, oops, v is going to be e to the t, right? That's my v. Okay. Oh, let me fix this a little bit. dv right here. Okay. So now I'm ready to plug this in. So t e to the t dt. I'm going to check, did I take care of all of my components? T, yes, and e to the t dt, that's my dv. So that means I have u times v. U times v. What is it? It's e to the t times t, okay, minus the integral of what? V du. So that's e to the t dt. Okay, that's nice. That's e to the t times t minus e to the t, and then plus constant, right? Let's call it C1. Okay, so that's our integration by part. That's my I component. Let's talk about J component. This is my first one. Let's do the second. Integral of t sine of t squared dt. Okay. What would be the method here? How would you integrate this one? You could do, yep, u substitution. Very good. Okay. If you need to set up u substitution, you could do that. So in this case, it would be what? It would be t squared, right? Okay. Or if you see how to undo this differentiation, you can just tell me what that is. And like when I was taking calculus 1 in Belarus, right? So we were not taught the u substitution. We were taught to mentally undo this integration, okay, or differentiation, right? So find that function. How do we undo it? So I'm looking at my sine t squared. What's the antiderivative of sine? It's cosine, right? Cosine of t squared. Now the question is, what about chain rule? So by chain rule, the derivative of the inside is 2t. Okay, 2t. I don't have 2t, I have t. So I need to divide it by 2, and also don't forget about the negative sign. Okay, so that would be my thought process. But u substitution is a little bit more well defined, right? So you can definitely use substitution here. We do not forget about C2. Okay, that's our antiderivative for J component. And what about K component? Okay, that's the integral of negative 2t. Here we get square root of t squared plus 4. Okay. Again, this is another u substitution problem. Okay, so you would have your t squared plus 4, that's going to be your u. Why is that? The derivative of t squared plus 4 is 2t, which is exactly what we have, right? 2t dt. Okay, and once you set up your u substitution and find the integral, you should get negative 2 square root of t squared plus 4 and constant c3. So our final answer is then a vector valued function, right? So our vector valued function, okay, let's call it capital R of t. What is it? First component is e to the t times t minus e to the t. Second component is negative 1/2 cosine t squared. And then the last component is negative 2 square root of t squared plus 4. And then I'm going to add that vector c, right? My constant vector c. So c is that vector c1, c2, c3. Now you could put those constants inside the components. That's fine too, either way, whichever way you prefer, okay? But just like with integration of regular um, regular functions, we do not forget about the constant. All right, so let me stop here for a moment. Take a look at this solution. Let me know if you would like to discuss anything. How do you guys feel about integration in general? Good, bad, indifferent? Pretty good, okay. Everything is clear about this particular problem? Move down. 1, integration by parts. 2, integration by u substitution. All good here? Okay, then let's move on to the next one. Okay, so here I have the same setup. Oh, I didn't give you the range of values, so let me go ahead and give you the range of t. So t goes from 0 to natural log of 2. Okay, let's go ahead and evaluate it. The first component is the integral from 0 to natural log of 2 of e to the negative t dt. Okay. So actually, let me go ahead and do it this way. I'm just going to integrate the entire function. Okay, so we go from 0 to natural log of 2. I'm going to integrate the whole thing. Okay, so what is the antiderivative? The antiderivative of each function here is easy to compute. We don't need to do any fancy methods. So the first one is negative e to the negative t, right? This is just undoing the rules that apply to exponential. So the next one would be just e to the power 2t. And then here we get the same value, negative 4 e to the t. We're going to evaluate this from 0 to natural log of 2. Okay, so we have two vectors. We're not going to get that, we're not going to get just a function, we're actually going to get a vector. Just like when you have limits for integrating a function, you get a number, right? Okay, so what is this? First vector is negative e to the power negative natural log of 2, and then e to the power 2 natural log of 2, negative 4 e to the power natural log of 2, minus this vector here. And just plug it in 0. Okay, and once we evaluate, what is the first vector? Negative goes up into that exponent for 2, right? So that becomes 1/2. And then we also have the negative in front of e. So the first component is negative 1/2. Then same idea here. So let me highlight these. Okay, that comes up here, that comes up here. 2 to the second power, that's 4. So this component is 4. And then here, this is just negative 4 times 2, so this is 8. And we get negative 1, positive 1, and negative 4 for the second vector. Now we just combine them. So what do we get? We get negative 3 over 2, and then 4 minus 1. So 4, oh no, that's actually positive. 4 minus 1, so that's 3. And then 8 minus 4. Wait, is this supposed to be negative? This is supposed to be negative, right? So negative 8 plus 4, that's negative 4. Okay, so that's our vector. Okay, all right. Is the first one 1/2? Yes, thank you. Let's fix that. I have it correct in my notes, and I was just going too fast right now. Yes, so this is negative 1/2 plus 1. That should be positive 1/2. Good catch. All right, so let's take a look at this. What it would do, we just integrated the entire function. So when do I do by component? When some of the functions can get a little tricky, right? So I just take a component one at a time. But if it's something so simple, we can just do the whole function at once, evaluate it. Once we have limits, that means we should get a vector as our final answer. Okay, take a look at this solution. Let me know if there's anything you'd like to discuss. All good? Okay, then let's take a look at the next logical problem that we would expect to see. If you were to take this class at FCC, you know that we talked about derivatives, we talked about integration, and then we talked about initial value problem. And that's what this problem is about. It says find the function R that satisfies the given condition. Okay, it might not be clear, but there's R prime here. This is prime, so that's our derivative. R prime of t is this function here, and we also have this initial condition that R of 0 is 2, 2, 2. So that's our initial condition. Okay, so this problem should be familiar to you. We've done it in Calculus 1, we've done it in Calculus 2, and if you've taken differential equations, that's a big problem there where we solve a lot of initial condition problems. Okay, just different form. Our function is a vector value function. Our initial condition is in terms of a vector, right? Where our initial point is not just a point in 3 space. It is a vector. Okay, but the computations are the same. So first things first, we're going to compute our integral. So what is R of t? It's the integral of R prime of t dt. So we are integrating which function? E to the t sine t secant squared t dt. Okay, all of these components are easy to integrate. The antiderivative is e to the t for the first component, negative cosine t for the second, and then antiderivative of secant squared, that's tangent t, plus this unknown vector. Okay, and that's what the initial condition is for. It is to compute this vector right here. That's the whole reason why we even have the initial condition. Okay, so once we're done integrating, we're not completely finished with the problem. Okay, R of 0 is a 2, 2, 2. So if I were to plug in t is equal to 0, okay, that's e to the 0 minus cosine of 0, and then tangent of 0 for the last component, plus c. I should be able to find my vector because I know what that is. It's 2, 2, 2. Okay? So now we can solve for this unknown vector c. Unknown vector c is the difference between these two vectors, right? So e to the 0, that's 1. Cosine of 0 is 1, so negative cosine of 0 is negative 1, and tangent of 0 is 0. So what is our vector c? 2 minus 1 is 1, 2 plus 1 is 3, and 2 minus 0 is 2. 1, 3, 2. We put it all together. What is our function r? R of t is, I'm going to put it all together in one expression. Okay, so r of t is e to the t plus 1, then negative cosine t plus 3, tangent t plus 2. So here, notice where my vector is. You can either put it in these components or you can just keep it outside. It doesn't matter. It's all the same. Okay, so let's take a look at this solution. Let me see. This is our initial value problem. Take a look at it. Let me know if there's anything you'd like to discuss. All good? You guys are quiet today. Let me know. Give me a thumbs up. Give me some sort of indication that I'm still with you. All good? All right. Okay, last problem for the day. Believe it or not, we will be done after this. This one says find the unit tangent vector at the given value of t for the following curve. So this is a curve that sits in 3 space, right? And for any value of t, we should be able to find, for any value of t where the function is differentiable, right? We should be able to find a tangent vector, but in this case, we also want a unit tangent vector, okay? So your general formula for this one, the notation for tangent vector is usually capital T, and we assume that's a unit vector. And it's r prime of t divide by the magnitude. Okay, and we evaluate our t of whatever the value that we're dealing with. So in our case, it's t is equal to 0. Okay, so we have all of the tools to solve this problem. Okay, r prime of t. Okay, derivative of sine is cosine. Derivative of cosine is negative sine. And then here we get negative e to the negative t. Okay, so we found our general expression for the derivative. Let's evaluate it at 0. Okay, this is cosine of 0, negative sine of 0, negative e to the negative 0. We get this vector 1, 0, negative 1. Okay, let me ask you this question. Is this vector 1, 0, negative 1 a unit vector? Okay, what do you guys think? Is that a unit vector? Kind of looks like a unit vector, but it's not a unit vector, right? Okay, Just because we have those zeros and ones there, that doesn't give us a unit vector. Now, if it was 1, 0, 0, or 0, 0, -1, then the answer would be yes, that's a unit vector. Okay? But actually, if you compute the magnitude of this vector, it is 1 squared plus 0 squared plus -1 squared, square root of this, at square root of 2, that is not equal to 1. Okay? And that is one of the common mistakes in this class that I see very often. You don't see that one vector with, we had just ones and 0 as your components, and you just go with it and say, oh, yeah, that's a unit vector, but not quite. It is only a unit vector if one of the components is 1 and everything else is 0. But as soon as you have any other component, 1 or -1, that's it. Okay, it's no longer a unit vector. So that's our magnitude. That's fine. We can still find our unit vector just by dividing by that square root of 2, right? Okay, so our final answer is t is a vector with which components? We got 1, 0, -1, divide by square root of 2. Okay, you can leave it in this form or you can redistribute that. So this is 1 over root 2, 0, -1 over root 2. And now this is a unit vector. Okay, it's actually a vector if you think about a unit sphere, right, in 3 space. Okay, then the ending point of this vector is on that sphere. Okay, that is your final answer for this particular problem. So take a quick look at this. Let me know if there's anything you would like to discuss. But that's it. We've covered everything that we need to know for the first 2 sections of chapter 14. And if there are no other questions, we can briefly talk about the exam. But let me know if there's any questions about this chapter. So let's go ahead and just go through what we've done. Okay. So for this last section in chapter 13, we should just um, have this sheet in front of us when we solve problems and should be able to determine by looking at the graph or by looking at equations what these objects are. Okay. Then we talked about sketching vector valued functions, just analyzing why these shapes the way they are. Okay. Computing limits. So that's a little bit of a calculus 1 review. And then determining equations of lines, straight lines in 3 space. Then finding derivatives of vector valued functions, which is done by components. Same for integration. Again, so this is just a little bit of calculus 1 review. And then the last thing that we talked about is determine unit tangent vector. Okay, so that's your quick summary of what we've done today. Um, take a moment, let me know if you would like to discuss anything at all. No questions, no comments? Am I still connected to you? Okay. All right, we're good. Okay, then let me go ahead and stop projecting this. And instead, I'm going to show you my my screen where I'm gonna go through just basic components of your test, right? So let me see where I want to go. I want to go to our course page, and it's nothing brand new that you haven't seen already if you open up that folder, but I want to do it anyway. So let's go ahead and share this one. Okay, let me know when you guys see the screen that just says test number 1. It might take a minute. Okay, you see it? All right, so on the left panel, you can see that now there's a tab, test number 1. Okay, with test information, so you can you can take it as early as today, and then it is available until Friday, September 17th. Okay, so this Friday. Okay, the time limit is 120 minutes. And my recommendation is for you to have paper, pencil in front of you, and you will be solving all of the problems on paper. Okay, so you're not going to be solving anything like you do with MyMathLab. You will see all problems at once. There are 10 questions. They come in the same order as we learned the material. So starting with chapter 12.1 and just going all the way to 13.5. Okay, all questions are in front of you right away. You will see the descriptions, you will see the statements of the problems, you will see how many points each problem is worth. Work on them in any way you want. And then when you submit your solution, so you would click here, paper solutions, okay? And just like you do with your quiz, right? So it's, I mean, I put it as it's worth 1 point. It's not really worth any points, okay? But you would get your files. If you want to make a comment, you can do it right here in write submission, okay? But when you actually look at the test, so when you will see the test, now I'm not going to start it here just yet. Um, there will be a field for each problem to enter your answer. And some of the answers are quick and easy. You know, if an answer is just a number, you can type it in. But if an answer is something like a function, Blackboard is not equipped with really good tools to type in math. So you can just say, see my paper. Okay, that's all you have to see. Say you either say, see my work on paper, or whatever phrasing you use, that's fine. Okay, so 10 questions. All right, submit your short answers on this test. And then once you're done, within 20 to 30 minutes, you know, I know some technical issues can happen, submit your work here. This is what I will be looking at. I will be looking at your handwritten solutions. So you want to make sure everything is included. They're nice and neat and easy to follow, okay? All 10 problems, if possible, it helps tremendously. Place them in the same order as the problems are coming. Okay, so try to organize your answers so I don't have to search for your problem. I will grade one problem at a time for the entire class. So problem 1 first, then problem 2, problem 3, and so forth. Okay, so it helps a lot if your answers are also submitted in that same order. Okay, so that's your test number 1. Again, I usually don't do any review packets of any type, but I am available on Thursday at our regular time. So we can use Thursday as a quick review if you feel like you need that time and you need to meet with me. So 11 till noon, that's a good time for you to just join and have any questions that you might have. That's not going to be recorded. So the Thursday sessions more of an, you know, pop in, have a question, solve it, and then, you know, you leave. Or you can stay as long as you need, but that's not a recorded session. Okay? If you feel comfortable with just taking the test, you go ahead and take it, and then you're done. There's no quiz for this week. So whenever we take a test, there's no other quiz to submit. Okay? So let me stop right here. Do you guys have any questions? Anything you would like to discuss? If there's nothing else, then we will stop our recording right now. And as usual, I will stay online until you guys no longer need me.